In this work, we present a new method for visualizing an image collection on arbitrary canvas shapes. Image collage is an essential tool for visualizing an image dataset. It is common in many applications. For example, social media platforms, like Facebook, automatically arrange users' photos into an image collage format when publishing. Photo managing apps on mobile phones display your photos in a compact and visually pleasing layout. There are multiple applications to choose from when you feel like creating your own image collage. However, as you can see, almost all of them only support fixed and rectangular layouts. When we want to create image collages that are more complex, we cannot find any available tools. That is why we start this research. Our goal is to create something like this. This is the results created with our method. The layout can be any shape. The content of the images are clearly visible. The image is arranged sensibly on the canvas. A possible way to achieve these results is by applying a mask to a rectangular collage. However, there are two obvious drawbacks. First, a large amount of information is heavily cropped. There are also small partitions that contain no meaningful information, especially on the boundary. A more sophisticated way is to adopt mass spring simulation-based tools. The downside, however, includes unclear shape contour, overlapping between images and blank space on the canvas. To design our method, we first go back to the literature on image collage. One key research topic is modeling the collage layout as a slicing tree. The tree root represents the whole picture. Each inner node represents a cut that divides one space into two. The number of leaf nodes equals the total number input images. Among them, soft collage is the current state-of-the-art method based on optimizing the tree via backpropagation. Another line of research tries to maximize the salient part of the image. We use these two research directions as guiding principles to design our method. Our system takes a shape and an image collection as input and outputs an image collage arranged in that shape. Our goal is to extend the existing tree slicing structure and the salient maximization concept to irregular layouts. Since the layout shape can be highly irregular, it is crucial to decompose the shape into convex parts. Otherwise, important content can be easily lost. We adopt the shape decomposition algorithm based on medial axis. The interior medial axis and external medial axis provide critical information to identify concave corners and the corresponding cuts. The resulting parts are called patches. Like the majority of image collage papers, we adopt the tree slicing structure. We initialize a tree with the number of leaf node according to the input images. The next question is how to map the tree slicing structure into an irregular layout, which we call shape-aware slicing. We observe that there are intuitive directions that are analogous to the vertical and horizontal directions. These directions are closely related to the medial axis. We define the axial direction as the direction parallel to the medial axis and the crosswise direction as the direction perpendicular to the medial axis. We cut a patch in half by drawing a line through its centroid in either of these two directions. Since the slicing tree is a recursive data structure, it suffices to discuss one recursive step. Using these simple rules we can achieve pretty good slicing quality as shown above. However, two things need to be noticed. 1. Because each patch is convex, the centroid is inside the patch. 2. Convexity guarantees that there are two and only two parts after the cut. If we don't run shape decomposition prior to our algorithm, like in the case of the letter C, our slicing algorithm will not work. Up to now, we only consider the shape. To achieve our saliency maximization goal, we need to also consider the content of the image. Specifically, we extract the salient object's bounding box and we let the user specify the importance of each image. We formulate the layout problem as finding the optimal slicing tree structure. The objective is to maximize the bounding box of the salient object as illustrated on the right. By enumerating all combinations of slicing trees, we can find the optimal configuration. The issue is that the time is exponential in terms of input image collection size. we proposed a speed-up strategy that reduced the exponential time to linear time. The idea is that the nodes near the leaf nodes is more important when maximizing total salient boxes. Imagine partitioning the canvas into 50 cells, whether the first cut is axial or crosswise is less important. Finally, we use a simple warping technique to fill the empty space. Now I have introduced our method, let's look at some examples to see if our method is actually effective. Compared to directly masking the rectangular collage, our method has no loss of information and no useless partitions. Our method also does not produce overlaps and blank spaces. Most importantly, the contour of the shape is clear. There are additional benefits. For example, compared to using Voronoi tessellation after shape decomposition, our method produces a consistent partitioning style. Furthermore, the style is consistent across different image collection size. This is the visual comparison of our results and the results from 4 other methods. Our method is superior in terms of both aesthetics and informativeness. TV and SHOP are simulation-based methods. SC stands for soft collage, which is the current state of the art. For the purpose of comparison, we also apply a mask to SC. In conclusion, we proposed a unified image collage on arbitrary shape algorithm centered around the medial axis. 3 main challenges are addressed with our slicing algorithm and optimal tree search strategy. We showcase our method with many examples and verify that our method is better than the existing ones. You are welcome to check out our paper and code on the project website and GitHub page.